Hello AP, we're going to learn Chapter 9, and Chapter 9 corresponds with Chapter 8 on drawing. But now we're going to draw the true shape. Just like the world, you, me, this pen, we're all three-dimensional, okay? So when you draw something like this, this is carbon tetrachloride, how do you draw something like this three-dimensional on paper that is two-dimensional? So with all of these shapes that you see, you notice how some of the bonds, and these are the bonds bend down, okay? So let me edge my camera down. So if I put this down, it kind of sits like a tripod. Notice it doesn't sit flat. If I push it down, it still, whoops, and I'm like bouncing molecules. It still doesn't sit flat. It still sits at an angle, okay? So what happens is, remember those things called lone pairs and electron-electron repulsion? Well, because of all these electrons that are around the halogens, because this is chlorine with all his 30-something electrons, and this chlorine also too, they have a lot of electrons. So what happens is they don't want to be near each other, so they have what's called repulsion. And because of that repulsion, the molecule has a certain type of shape to it called tetrahedral. So in this chapter, we're going to start to learn the shapes of molecules. We're going to learn their names of the shape, the bond angle that you see right here. So from here to here, it's a certain bond angle, from here to here. And just like with water, this is water's true shape, okay? But why aren't the hydrogens going straight out like we would draw on paper? Why is it bent? Well, you got to remember, what does oxygen have up here? Called lone pairs. Remember I told you lone pairs, they pretty much bring everything away from it. They want all this space that's up here. So this is what's the shape of water. It's a true shape. It has what's called a bent shape. So just like this one, we're going to learn the bond angle that's between this shape too. So in the next couple of videos, I will probably have the camera on because I'm going to build these molecules. And usually with the lab that we do, the lab is you would build it in the lab and then you draw what you see. So that will be one of the next upcoming labs that we do. And it has to do with Chapter 8 and 9. So it's kind of like two birds with one stone. So I'm going to bring it back to the notes. Okay. And 9.1, very short. So we can understand the point of why we need to learn all these three-dimensional shapes and angles. So in Chapter 8, we learned what's called Lewis structures. The problem is Lewis structures, that's two-dimensional, okay? It's not the proper shape. It's not the actual realistic shape or angle of that molecule. So Lewis structures do not show one of the most important aspects of the molecule, and it's its true shape. There are so many different shapes to molecules, it just depends on how many bonds and lone pairs that they have. So the shape and the size of the molecule, sometimes referred to molecular geometry, very important name coming up, okay? So I'm sure you heard the word geometry before in math class where you're looking at different sides and angles, and we're doing the same thing, but we're just doing bonds and electrons. And it's defined by the angles and distance between the nucleus and the corresponding atoms that are attached to them. So depending on if it looks like something like this, carbon tetrachloride, or is it the true shape of carbon tetrachloride? Oops, sorry. Or is it the true shape that looks like this? Okay. So when you draw this, we have to take into account its actual shape that we see it in the world. Because as you see right there in the notes, that is carbon tetrachloride when we drew it back in Chapter 8. But what is this real shape on paper? So our first goal is we have to understand the difference between two-dimensional and three-dimensional. The shape and size of a molecule of a substance together with the strength of polarity. I told you it's coming back with a vengeance. So we're going to look at shape and size and polarity. And that is like really bad highlighting right there. Sorry, I'm doing it with my mouse instead of the pen. With that polarity, are they being shared? Is it being shared equally or not? So is it equal sharing or not? And it largely determines the properties of that substance. So when we look at two-dimensional versus three, we have to examine the nature of the bonds. The lines used to depict bonds in Lewis structures provide important clues about orbitals. And we're going to be talking a lot about s and p orbitals. Because we're not talking about metals at all in this chapter, we're not bringing in the d's and the f's into this. So it's all about the s and the p orbitals. By examining these orbitals, we gain a greater understanding of the behavior of the molecules, especially when it comes to polar and nonpolar. Because if you ever want anything to ever dissolve in water, it has to be a certain polarity. So take the example of carbon tetrachloride. And on paper, that's how we would draw it. Carbon, 4 bonds, 4 chlorines. Chlorine's got 7 valence electrons. So when you do the NaOH, you'll get 4 bonds. But that it's this true dimensional shape. In reality, as you saw, this is this 3-dimensional shape. So he takes what's called a certain shape called tetrahedral. Tetra meaning 4. So it kind of looks like a tripod. If I put it like that, as you see, the carbon is not in the same plane as the paper, as the hand. So they sit, all of these carbons, they sit at a certain angle. And just like if you look at it this way too, kind of looks like almost like a triangle type of pattern. The problem is though it has 4 bonds. So it has not a 120 angle, but it's actually about 109. So yes, we have to learn some angles and some names. So with this carbon tetrachloride, it's called a tetrahedron, but we call it an AP, tetrahedral. And with the 4 corners and 4 faces, okay, like I said, kind of looks like a pyramid, but each one of these carbons and chlorines, they all have a certain bond angle, and right here to right there. So that bond angle. So if you're looking at this molecule, from here, going all the way down to one chlorine to the next chlorine, you get about a 109.5. And AP is totally fine with you just saying 109. 109 is just fine. You have to be specific, 109.5, but that's the true angle. So from here to here is 109. And then if I turn it this way, here to here is 109. If I flip the molecule this way, 109 going that way also. So all over this molecule is 109 degrees. And make sure when you do bond angle, you do put that little degree sign in the corner because you're talking about a degree. You're talking about a measurement, okay? So this is what's called the ball and stick model. As you see right here, ball and stick. And then you have what's called space filling, where the space filling is actually taking into account the size of the atoms, okay? So because chlorine is bigger than carbon, as you see these giant, more type of circular shapes for the chlorine, compared to the dark circle that the carbon is. So like I said, when we do the lab for this, we're going to start looking at colors too. So every time you see black is carbon, every time you see green is a halogen. It can be any halogen. Oxygen's always red, hydrogen's always white, blue is always nitrogen, and so forth, so forth. So we're going to start learning some colors too of the molecules. So the shape of the molecule is determined by its bond angle. Okay, so the angle made by the lines joining the nucleus of one atom in the molecule. So we're always looking at the central atom. The central atom is always the star of the show. So the bond angle from one atom going down to the next atom. That is the bond length or bond angle. Just like with water. The bond angle is from this hydrogen going all the way to that hydrogen. And for water, it's 104.5. Okay, which AP would allow you to say either 104 or 105. Okay, so we started to look at bond strengths in chapter 8.8, call that bond enthalpy. And the higher the value that delta H, the stronger the bond is. Because that's why you need more energy to break it. So bond enthalpy, those delta H values, the higher the value, the stronger the bond is. So now in chapter 9.1, we're able to see that there are 6 Cl-CCl bonds. And you're probably looking at, wait a minute, where's the 6? Okay. When it's tetrahedral, it's got 4 atoms. Okay. Well, you got to remember, you have from here to here is 1. From here to here is 2. From here to here is 3. And then when you flip it upside down, you also have these ones right here. here, here, and here. So there's actually 6 of them on there for something with just 4 atoms. So between every single one of those ClCCls, it's about a 109.5 degree angle, and it has a shape name. Like I said, we're going to call it, oops, right there, tetrahedral. That's the name we're going to call it. Tetra meaning 4. So what if it has 3 or 2 atoms or 5 or 6 atoms? Well, then they all have their different names and angles, and we're going to learn them. So all 4 bonds have the same length because they don't have lone pairs. And no, we're not going to learn bond lengths, but we are going to learn bond angles. And because of that bond angle is corresponded to a tetrahedral. So every time you have a tetrahedral, always has that bond angle of 109.5. So in this chapter, we're going to examine shapes, we're going to examine angles, and names of those shapes. So if you have molecules like with the formula ABN, and that N could be any subscript, where A is the central atom and B are the atoms that are surrounding it, like CO2 or water. Because they have 3 atoms, so like CO2 would have a double bond, and we already know what water is going to look like, but they don't have the same shape. Okay, this is what water looks like. Okay, but with carbon dioxide, it has what's called a linear shape. Okay, where the carbons and oxygen, they're lined up on a line. Water doesn't do that because there's lone pairs sitting on top of it. So ladies and gentlemen, we draw it on paper first so we can actually get a picture, an image of what it's actually going to look like. And then we help build it, which I'm going to help you build it, so that way you can actually see the true shape. You can visualize what it actually looks like. So the number of shapes are possible as N increases. So the more that N increases, the more shapes possible you could have. So if I have a 3 or 4 or 5, I can get different types of shapes. And by doing this, ladies and gentlemen, this whole looking at shapes and 3D, it has a certain name in chemistry, and it's called VSEPR, valence shell electron pair repulsion. And what VSEPR is looking at, it's looking at the central atom, and it's looking at a couple things: the bonds that surround it, and it's also looking at the lone pairs on the central atom. Okay, so the bonds that surround it, and I think I crammed that in there, sorry. Surround it. And the lone pairs that are on the central atom too. So the more lone pairs, this carbon has no lone pairs on it, but this oxygen has 2 lone pairs. So the more lone pairs you have, the more it's going to change the shape. So we call this model, we call it VSEPR, valence shell electron pair repulsion. And what this model is it tells us the true shape name and the true bond angle for any molecule that we use. So 9.2 is coming next, and we're going to go through every shape and every angle. So 9.2 is going to obviously be a little bit longer video than this very short one, but I'm just letting you know what's coming our way. So we get a little bit of review of chapter 6, some S and P orbitals. We're going to get some chapter 8, more practice with drawing. And we're definitely going to get more practice, and I know Miranda, you're going to be happy, of polar and nonpolar. Okay? So I'll see you on the next one, 9.2.